actually grew up here in the Bay Area. I was born in Berkeley in Alta Bates Hospital, and when I was about 4, we moved all the way to Albany. And I went all the way through the Albany Public Schools. So this is essentially me coming home, being back here in Berkeley. I've been a research fellow here for the last 2.5 years. I've got 1 more year to go, and then I head off to the next phase, and I don't know what that is yet. I'm applying for jobs right now, so we'll see. I did my thesis work at UC Santa Cruz, working with Sandra Faber there, on galaxy evolution and studying galaxies in the local universe in particular. What I'm going to talk to you about today is to try to give you a large-scale picture of what galaxies are, how they relate to us in terms of the sort of scales that they occupy versus the scales that we occupy, which are very different. And in particular, I want to convey the fact that galaxies are not static. They are entities that evolve in time on very slow, very long time scales, but they are continually changing their character. And our galaxy today is not going to be the same as our galaxy in the far future. So this is a look at how those processes happen in galaxies. How many of you guys have been out on a dark night somewhere far away from the Bay Area and actually seen the Milky Way in the sky? Okay, good. So most people, if you haven't done it, you should take the opportunity sometime when you're driving across the desert. You need a dark night because it's quite faint, but you get this spray of kind of faint, wispy stuff across the sky. This is an image that was taken in the desert in Arizona. And if you look at it with your naked eye, you see something that is black and white. You basically just see there are places where there's light and places where there isn't light. And that's in part because your eye is, the color sensing part of your eye is not very light sensitive. So in faint conditions, you basically see in black and white. But if you have a digital camera and you can take an extended time exposure, you can actually get colors. There are actual colors in the Milky Way, and things look quite different when you add color. So now we can see that, I'm going to turn the lights on a little bit. Right, so you can see that there are bright patches and then there are dark patches in the Milky Way. And there's this it's a streak across the sky. We even have these little clumps of bright red light that are scattered through there. Some of the light looks bluer, some of the light looks yellower. So there's a whole bunch of different stuff going on in the Milky Way. And that's in part what we're going to explore today, is what all these different components of our galaxy are. All right, so just a very brief outline. We're going to start by just talking about what is a galaxy. And then go on from there to think about what galaxies are made of. What are all the different components that exist in galaxies, and how do they relate to one another? And then move on to talk about essentially how do you make a galaxy? Where do they come from? How do they form? How do they evolve with time? And how do you make different kinds of galaxies? Because not all galaxies in the universe look the same. And then finally, we're going to end with a little bit of context, just trying to understand where galaxies are in the universe and how many of them there are out there. All right, so what is a galaxy? Well, just to start with some sort of scale perspective, we're going to start with something that is hopefully a familiar scale to everyone. I'm going to turn the lights down again here. Which is the planet Earth, right? If you've been on a long plane flight, you have experienced, to some extent, what the scale of the Earth is. It's big, but you can get around it. We can move around it in human amounts of time. What we're going to do now is zoom out from the Earth that is this familiar place to us and look at how it fits in to the Milky Way galaxy that we were seeing there on a dark night in the desert. What this is showing you right now are the orbits of various man-made satellites that we've launched into space that are orbiting around the Earth, some of them in close orbit, close in, and then some scientific instruments that have larger orbits farther away from Earth so that we can get them out into darker parts of the sky. If we keep zooming out, you can see there the moon traces out an orbit around the Earth that looks big compared to all the satellites, but then when you start to scale out toward the scale of the solar system, it's really quite small. The moon is very close by. So continuing on, now we're looking at essentially the entire scale of the solar system. This is about 1 day's worth of light travel time. So light takes about a day to get from the sun outside of the solar system. And as we move outwards, eventually we're now only just now getting to scales where we can actually see other stars moving with respect to the Earth. So essentially, the stars are all so far away that you have to go to very large distances before they actually start to look like they're in different places in the sky. And you can see that as we sort of zoom out here, we're in this collection of stars that is producing a bunch of light, which from a distance looks quite smooth. But if you actually go in and focus in, all of that light is coming from hundreds of billions of stars that are packed together in the Milky Way galaxy. Then what happens is if you get out far enough, there aren't any more stars. These dots are actually maps of other galaxies in the universe. So the stars really are concentrated within a galaxy, and then in between galaxies, there's very little. We don't really see anything there. So they are sometimes referred to as island universes. There's this island of stars that are self-connected, but that are isolated from other things in space. So a challenge was trying to study our own galaxies, but we're in the middle of it. So we don't get a very good picture of it. We can't see it from the outside from a wider perspective. We just see kind of close in what's going on, and we have to look through a lot of junk to see what's going on. So one way that astronomers study our galaxy is actually by going to a separate galaxy. So our nearest neighbor, the Andromeda galaxy, is part of our local galaxy group. Like the Milky Way, it's a spiral galaxy. It has many similar properties. So what's nice about it is it makes a good proxy for studying our own galaxy, because we're outside of it and we can see it from that exterior perspective. However, if we put back up this picture of the Milky Way here, we can see that there's a lot of similarities between these galaxies. When we see bright patches that tend to be sort of yellow or red toward the center of the galaxy. We see bluer light coming from stars farther out in the galaxy. We see that in Andromeda, and we can kind of map that mentally onto what's happening in the Milky Way here. We also see these dark clumps in both galaxies. In our own galaxy, we just see these dark bands. If you then look at Andromeda, you can see that those dark bands are actually distributed in spiral structures and in the spiral arms of the galaxy. And the other thing is we also see these bright pink knots of glowing gas. And we see that both in our galaxy and in the Andromeda galaxy. So there are many ways in which Andromeda is a good proxy for studying our own galaxy. And we can see it from the outside, so that helps us try to understand what's going on in our own galaxy. Right, but not all galaxies look the same. This is just a gallery of Hubble Space Telescope photos of various galaxies in the relatively nearby universe. And you can see, like, the galaxy in the middle there is one that's like the Milky Way or Andromeda, has spiral arms, has spiral structure. We see these dark dust lanes. But there are galaxies that look very different from that. So when we ask the question, what is a galaxy, and try to define the properties of a galaxy, we need something that's going to encompass this wide collection of objects, many of which look quite different. And ultimately, we would like to understand how the universe makes these different kinds of objects, how they relate to one another, and what are the differences in the formation processes that make something like this smooth red galaxy down here that doesn't seem to have dark clumps in it, doesn't seem to have bright knots, as compared to something like this spiral-shaped thing over here, which looks very different. Just to emphasize, if you look at galaxies kind of in their natural environment, they're quite spread out. Right? You have galaxies that are collected nearby each other, but then in between them, there's not very much. And in fact, you do see individual stars here in between these galaxies. These stars here are all stars in our own Milky Way. Right? So we have to look out of our galaxy to the distant universe, but every single one of these stars that you see in the foreground, they're not out there at the same distances as these galaxies. These are a foreground screen of stars that we're looking through. So if you sort of mentally remove those stars, what you have is a group of galaxies, and you have very little stuff in between them. So they really are these islands unto themselves, illuminating the dark spaces of the universe. All right, so what is a galaxy? Let's see if we can have a sort of a simple definition that encompasses the wide range of objects that astronomers see and call galaxies. The way I'd like to define a galaxy is that it's a collection of stars that are bound together by their mutual gravity. So this is a place where you have, it's a large collection of stars, tens, hundreds of billions of stars, that are held together simply by the gravitational attraction of all of those stars to one another. So these stars they're bound in and they're orbiting the center of the galaxy and orbiting in the gravitational pull of all of those other stars. Okay, we're going to add a caveat to that later, but we'll come back to that. All right, so in order to call something a galaxy, we're going to require that it be a collection of stars. All galaxies have to have stars. If it doesn't have stars in it, we don't call it a galaxy, and we don't see it as a galaxy. But there's a bunch of other things that you find in galaxies. And not necessarily all of these things in any given galaxy, but many galaxies contain these things. So we see gas, and we'll look at pictures of that, some evidence for that later. We see dust, so dark clumps of stuff that absorb light along the line of sight. We see star-forming regions, places where new stars are being born. And then one thing that has come out in the last 10 years or so is that most galaxies, certainly the large galaxies, harbor a very massive black hole at their center. So this is actually, and the properties of this black hole are closely linked to those of the galaxy it lives in. So our understanding of what galaxies are and how they form and evolve seems to be intimately related to the presence of these very massive black holes. So let's take a closer look now at some of these ingredients that go into making a galaxy. So the obvious first thing to talk about are stars, right? So we see this band of light in the sky that we call the Milky Way, and we see bright patches and dark patches. But the bright patches look pretty smooth. It's not obvious where that light is coming from or whether it's coming from multiple different sources. But if you zoom in with more and more powerful telescopes and into these bright regions, what you see is eventually they resolve themselves into individual stars. So all of this light that you're seeing here is being produced by individual stars that in some cases are just packed so closely together. You're not resolving them with your eye. You can't even resolve them with small telescopes. But if you go into space, you can see that, and zoom in, you can see that all of this light is actually coming from discrete sources, individual stars that are all grouped together, that are producing the light that we see in these galaxies. So I'm going to take one step back and just talk a little bit about what stars actually are, because they're the most important constituent of galaxies and most of what we see when we look at galaxies. Okay, so a star is just a giant ball of glowing gas that has several properties. This picture here is a picture of our sun. So that's what the sun looks like close up. It's a much scarier thing than the normal light that we see just when we go outside and look at it. All right, so a couple of points about stars. One, they're powered by nuclear fusion. All of the light that's coming out of the sun is energy that is generated by essentially a hydrogen bomb in the center of the star that is continuously fusing nuclei together and releasing energy. So that's where all the energy comes from in the star. Stars are held together by gravity. So essentially, the gravity, the self-gravity of that big ball of gas is pulling all of it in, which is important. You need that pulling in to hold it together because the radiation that you're making from nuclear fusion in the center produces a pressure of photons of light traveling out of the star that would blow the star apart if it weren't balanced by gravity. And stars actually self-regulate. The gravity and the radiation pressure coming out of them create an equilibrium state. And if gravity if the star starts burning a little less quickly and gravity starts to win, it pulls in a little bit, but then that makes the center heat up. And it starts fusing nuclei faster, it gets hotter, produces more radiation, and that pushes it back out again. So it's this equilibrium system that self-regulates a balance between nuclear fusion in the center and gravity on the outside. Another point that was not immediately obvious, and that astronomers only really figured out in the early 20th century, is that stars are made of the exact same elements that we see here on Earth. So there's nothing special about the material that's in the sun or in other stars. It's the same stuff that we have here. And the way we know this is that if you take the light coming out of the sun and you put it through a prism, you spread it out in wavelengths, you have red light at one end and blue light at the other end, These are a nice spectrum here. You can see if you look closely that there are actually there are these places where the light is a little dimmer, right? These sort of dark patches in the spectrum. And here, this is just this plot down here. It corresponds to these wavelengths here, and it's just showing you the intensity at each wavelength. So we see these places where essentially there's a big drop in how bright the light coming out of the sun is. And these are specific absorption features that correspond to individual atomic transitions. What's really cool about these, and this is actually, I spent a lot of my thesis work studying these aspects of stars, is that they essentially are a fingerprint of the materials that are in the star. So if you go to a lab on Earth and you take a big ball of hydrogen, and you look and say, well, what does the spectrum of hydrogen look like? You see these strong individual absorption features that give you this characteristic, they have a characteristic spacing in wavelength, and they're giving you a characteristic fingerprint of what the hydrogen atom looks like. What we see is if we then look closely in the sun, we see those exact same absorption features in the sun that we see in hydrogen here in the lab on Earth. So this is essentially the fingerprint of hydrogen in the spectrum of the sun, telling us that the sun contains hydrogen. We also see there's other lines that are not hydrogen, that are things like sodium, iron, magnesium, calcium, carbon, nitrogen. So we see other elements, and by identifying these lines, we can actually we can measure the chemical composition, how much of these different elements exist in our sun and then also in other stars. And we see these same patterns everywhere we look. So stars in our own galaxy, stars in other galaxies, we see these same sets of fingerprints of the basic atomic elements. And that tells us that our sun, the stars in our galaxy, the stars in other galaxies are made of the same sets of basic elements that we see here on the Earth. All right, so those are stars. So the stars are producing all this bright stuff that we see in the Milky Way. But then we see these really big dark patches. So these dark patches are not actually an absence of stars. What they are is they're big clumps of dust that are obscuring light from background stars. So we're sort of looking along a sight line, and we see, and then we hit this wall of dust. So how do we know that? Well, if we look in the visible light, this dust is very good at interfering with visible light photons. But if we then move into the infrared to longer wavelengths that are actually less, that don't interact with the dust as much, we can actually see through those clumps of dust. So we can see when we look in the infrared, it's not that there are no stars. We can see those stars behind the big clumps of dust. It's just that the light from those stars is being absorbed before it can get to us by the presence of this foreground screen of dark, opaque dust that absorbs the light. So when you next go out on a dark night and look at the Milky Way, it's being able to envision it as this band of light, this enormous collection of stars and these obscuring foreground clumps of dust is I think for many of us, an unfamiliar way of thinking about it. One of the nice things about being an astronomer is that the telescopes that I use for some of my work are the Keck telescopes on Mauna Kea in Hawaii. So this means that I am required for my work to travel to Hawaii with somebody else paying the bill. And my husband now has a rule, which is that when I go to Hawaii, he gets to come too. I'm not allowed to go without him. So the last time we were there in August, I had an observing run at Keck, and we went out for a drive on a clear night after I was done observing, and we pulled over and stopped by the side of the road. We were in the middle of nowhere, no lights, very dark night. And of course, astronomers use Hawaii as an observing site because the sky is so clear. And we saw the Milky Way there smeared across the sky. And we were talking about the light parts being made up of stars and the dark obscuring dust that gets in the way. And the fact that all of the other stars that we see in the sky are the parts of the Milky Way that are near us, and then we're sort of seeing this band is the more distant part of our galaxy. And he suddenly had this vision of it like he was looking out into his back garden. And this is our back garden of the sky. And the individual stars we see are like the nearby plants that we sort of plant right outside our back door on the patio. And he had a sense of looking down, and essentially this is sort of being the bottom of the garden. the distant end of the garden with the fence, and then out beyond it is the sort of the emptiness that is not us, that's not home. It's the stuff beyond the garden fence. So that is our Milky Way galaxy, our garden. Here's another view of the dust that's obscuring light in our galaxy. This picture on the left here may be familiar to a bunch of you. It's one of the most famous images taken by the Hubble Space Telescope. And what you see in it is this big pillar of dark dust. And it's obscure. You don't really see stars shining through it. And you actually see light scattering off of it. You can see almost these, in a sort of tenuous regions here. Again, if we look in the infrared, we can see through the dust. And we see that behind that dust, there's plenty of stars back there. We just can't see them because they're being obscured by the foreground light. So one of the things that's interesting about this comparison is it highlights something that is true across astronomy, which is that when you look with different wavelengths of light, you see different things. That's a very powerful tool that astronomers have used to study things in hard-to-see regions or over large distances, and to kind of tease out the different physics that go into these different components of astrophysical systems. All right, so we've now talked about stars, right, all the little bright dots here. And in this image here, we've got some very bright young stars that have just formed. And we've talked about the dust that makes these obscuring foreground regions. So here, this is an image of the Horsehead Nebula, which is another relatively famous astrophysical object. So you can see the dark horsehead-shaped thing obscuring the background light. But then there's also all of this glowing, diffuse light. Then this light here is actually not coming from stars. This is coming from hot, glowing gas. So this gas, again, we can ask, what is this gas made of? We can bring back our spectrum of hydrogen from the laboratory on Earth, and we can then take a similar spectrum of the gas, basically take this light from the gas, put it through a prism. And what we see is we see specific, very intense, strong emission lines in the gas that correspond exactly to the emission lines that we see in hydrogen in the lab. So this gas here is basically hydrogen. There's a few traces of other elements in it, but what you're seeing here is a giant cloud of hydrogen that is being heated up by those young stars that have formed recently. And that gas then glows at specific wavelengths. So galaxies, like the Milky Way, also contain gas. Hot gas, which is glowing and which tends to be clustered around, or is heated up and ionized by these young stars. So we tend to find that around young stars. And it has a characteristic color, right? So what you're seeing here is the red of this specific hydrogen transition line, which is called the H-alpha line. And that gives it that characteristic color. So then when we have our picture of the Milky Way, you see those bright kind of pink spots that have a very specific color that are scattered through the clumps of dust. That pink color corresponds to this transition here. But the hot gas is, in some ways, is the easy gas to see, or it's the gas that we can see in the visible light range. But there's also cold gas in the Milky Way galaxy, and in other galaxies. So the cold gas you have to see by going into the radio and observing at radio wavelengths. Because the gas is cold, you're only able to see very low energy transitions. So this is actually what Steve does. He's a radio astronomer. And we can use radio waves to map out where the cold, dense gas in galaxies happens to be. What we see is that the cold gas traces out these spiral patterns. So we tend to find cold gas clumped in the spiral arms of spiral galaxies. And it tends to be, we find it in the same regions where we find a lot of the dust. So the cold gas and dust kind of hang out together in the galaxies. All right, so we've been asking this question, what are galaxies made of? We've seen that galaxies contain a lot of stars, right? That's what's providing the light, most of the luminous, visible light that we're seeing coming out of these galaxies. We've also seen that galaxies contain dust, these dark, obscuring bands that we can actually see just absorbing light and making dark patches in the galaxy, obscuring the stars that lie behind them. And where we see dust, we often also see cold gas. So the dust and the cold gas go together. We also see that the galaxies or some galaxies at least, have these hot bubbles of red gas that are glowing with specific transition lines of hydrogen. And that these tend to be clustered around young stars that are in the process of forming. Right, so now if we go back to our gallery of galaxies, we can see that not all of these galaxies contain all of those components that we were just talking about. Some of them really have very obvious, strong dust absorption in them. Some of them are pretty much dust-free. Some galaxies have cold gas in them when you observe them in the radio. Some galaxies are, lacking cold gas. Some galaxies have these little kind of pink knots of star-forming regions of hot gas. But again, not all galaxies have these things. So if we come back to this, our little kind of breakdown of what goes into a galaxy and how do we define a galaxy, well, galaxies must have stars, and we see stars both in the disk part of the galaxy and in spiral arms, but we also see stars in these more spheroidal objects. Right? All of this light is coming from stars. But these other components may or may not have to be there, right? So gas, we tend to see, we see those hot gas bubbles mostly in the disk. We see cold gas in the disks of galaxies. Dust, we tend to see mostly in the disk, and even in galaxies that don't have a big stellar disk, when we see dust, the dust itself seems to be in a disk-like form. Or that guy in the upper right-hand corner, right? The dust seems to be in some kind of disk-like pattern. And we've seen that these star-forming regions tend to happen in the disk part of the galaxy. Right? If we go back here and say, where are the little pink knots of stuff? We don't see them in these smoother galaxies. We see them in these things that have clear spiral arms. All right, so the piece that I promised you about that I haven't talked about yet is the idea of a central black hole. We think that these exist in lots of galaxies. So the easiest, or the first place to look for such a thing is in our own Milky Way galaxy. So what happens if you look toward the very center of the galaxy, which you can't actually do from here because the center of the galaxy is in the southern hemisphere. There are many astronomers who believe that we would have understood galaxies sooner and a lot better if it hadn't been true that the galactic center were in the southern hemisphere, far away from where most astronomers were viewing the sky up until recently. So if we zoom in on this central region and we can actually see and resolve individual stars at the very central part of the Milky Way galaxy. And what's nice about the center is things are so compact and so dense, we're looking at small scales, we can actually track the stars there over time. So this is a movie starting in 1995 that's then tracking the location of individual stars in the galactic center over a period of about 15 years. And what you can see is that, particularly if you watch toward the central region where there's a little white star symbol, is that these stars seem to go there and then they kind of deviate, right? Their orbits kind of loop around. And by tracking the orbits of these stars, we essentially can make a mass measurement. We can see that they're orbiting around something, and the speed and the shape of the orbits allow us to actually measure the mass of the object that they're orbiting around. So even though we don't see anything there, there's no visible star, there's just a little kind of star character that's been put on there, we can measure the presence of an enormous mass. So that is a black hole that is 1 million times the size of the sun in terms of its weight. Of course, it's much more compact than the sun, but the weight of that thing there that's controlling the orbits of these stars is 1 million times the size of the sun. And it's sitting there, right at the center of our own galaxy. But, it's not really doing very much. It's a black hole. It's kind of sitting there. Black holes don't go around like vacuum cleaners sucking in everything that they come across, right? It's just a mass. And just like our planet, our Earth goes around the sun, stars orbit around another mass. And the black hole just behaves like any other mass, unless you get too close. So we see it in our own galaxy. What about other galaxies? When we go out, we can't observe individual stars in the central parts of galaxies, so we have to use somewhat more indirect techniques. But when people go out and when astronomers go and look at other galaxies, they find evidence for massive black holes in the centers of them as well. And what's really interesting is that the size of that black hole, when they weigh the black hole and say how massive is it, the mass of that black hole seems to know about the mass of the galaxy. So there's a strong correlation between the mass of that central bulge of stars, which is what's being plotted on the x-axis here, versus the mass of the black hole mass. This is the central black hole mass, which is on the y-axis. So bigger galaxy bulges host bigger black holes. And this is a nice schematic drawing, but this is actually what the data looks like. This is taken from a recent scientific paper on this topic. So again, plotting just the map, how big is the bulge of the galaxy? And the scales are larger. Right? This is 1 billion times the sun, 10 billion suns, 100 billion suns. So these galaxies are big versus the size of the black hole that sits in the center. So the black hole, if you have a billion solar mass galaxy, you have about 1 million solar mass black holes. There's a factor of 1,000 difference here. But that means that the black hole is about 1,000th the size of the galaxy that it sits in. So it doesn't dominate. The orbits of the stars in the galaxy are not, they're mostly feeling the other stars. The black hole is only a small fraction of what they feel until you get right down to the center near where it is. But it's non-trivial, right? It's not some little thing along to the right. It actually is a significant piece of the galaxy. It's about 0.1% of the galaxy. All right, so back to our list of what's in a galaxy. Galaxies have to have stars. We've seen that a lot of them have gas or dust or star-forming regions in them. Many of them, massive galaxies have these central black holes, and the more massive the galaxy is, the bigger its central black hole. But I said there's a caveat that we were going to apply, because there's something really big missing from this list of galaxy ingredients that actually dominates many of the properties of the galaxy. And that is the dark matter. Right? So when astronomers go out and observe galaxies, there's evidence that we're actually missing some of the mass in the stuff that we can see when we look at the light coming out of stars, and count up all the stars and account for all of the gas in the galaxies, that we're missing a big component. So how do we see that? Well, okay, so say you're here, you're the observer, you are the all-seeing eye, and you are looking at a galaxy. And you're looking at a nice spiral galaxy, and that spiral galaxy is rotating. So one part of the disk of the galaxy, the stars are mostly moving away from you, and then on the other side of the disk, it's rotating, the stars are moving back toward you. Because things are moving toward you and away from you, you wind up having a Doppler shift of the wavelengths of light that are coming out of things. So just like when a fire truck comes down the street and it comes toward you and then passes you, it's kind of sound. The pitch goes up and then drops again. It's because when it's coming toward you, the Doppler shift, the sound waves are shifted to higher frequency, and then it moves away from you, they're shifted to lower frequency. So if you have some kind of feature in the spectrum, you can identify some particular wavelength of something that's going on. What this means is that the part of the galaxy that's moving toward you, that line will be shifted to the blue by the Doppler shift. The part that's moving away from you will be shifted to the red by the Doppler shift. And what that does is that gives you a way of measuring the speed of rotation of the galaxy, because you can measure the shifts in those lines, and you then know how fast the galaxy is rotating. So what that tells you is, right, you've got some mass here, you're out here, and now you can measure an orbit. You can measure the orbits of those stars. And being able to do that allows you to weigh the amount of mass inside the radius that you're probing. So if you can measure the speed of a star moving here, you know how much mass it's moving around. Okay, so then you can say, as a function of radius, you start at the central part of the galaxy and move out toward the large part of the galaxy. You can essentially, measure how fast the stars are moving as you go out. That's what's plotted on the y-axis. So as you go out, right, you've got more and more stars in the sense, as you move out, there's more stars that you're orbiting around. So you start orbiting faster and faster. And the little circles here show you how fast stuff is moving in the galaxy. But then we see the light from these stars. So we can kind of count up the number of stars and turn that into a measurement of how many stars there are, how heavy, how much mass there is here on the inside, and say, okay, well, given the amount of mass that we see, how fast should the stars be moving? And that's this solid line. So what happens is you get to the outer part of the galaxy and you run out of stars. And if you have something like cold gas that's letting you trace farther out, or globular clusters, or some other kind of tracer, you see you've run out of stars. The amount of mass is dropping, and the orbits are getting bigger. So the velocity of the orbits should be dropping. and it doesn't. So there's extra mass hanging out. If our theory of gravity is correct, there's extra mass hanging out in the outer parts of galaxies, and you can see it in its effect on the orbits of the stars, but you don't see it in light coming out of stars. This is just one of the pieces of evidence for dark matter. There's many others coming from different directions, and so you put them all together, the case is pretty compelling. I'm not going to try to convince you that dark matter exists at the moment. You'll have to come back next month and hear a whole talk on that. So I'm just, from the perspective of galaxy formation, I'm just going to assume that the dark matter exists. This is our current best theory for what's going on in the outer parts of galaxies. And it's not a trivial component. The dark matter is 90% of the mass in the galaxy. Not in the center. In the center, you're dominated by stars. But as you go farther and farther out, more and more of the mass is made up of this dark matter. And on large scales, it completely controls the fate of the galaxy. So the dark matter is a very important part of how galaxies form. All right, so that brings us to the recipe. We now know what goes into our galaxy. How do we actually put it together to make a galaxy? So to do this, we're actually going to do this using computer simulations. We're going to start with the current standard cosmological model, which is called cold dark matter with the cosmological constant. We use the capital letter lambda to represent the cosmological constant. So this is sometimes called a lambda CDM universe. Right, so in this picture of the universe, atoms, the normal stuff that you and I are made of, that we encounter on Earth, is only 4% of the total mass energy budget of the universe. Most of the matter is actually dark matter. So that's about 23% of the total stuff in the universe. And then most of the universe is this mysterious dark energy that we don't actually really know what it is. And we don't really know what the dark matter is either. But I'm going to give you what is actually a simple model. Okay, it sounds like, okay, we're invoking all of this mysterious stuff. That sounds very kind of complicated and tricksy. But it's actually a simple model. What we're going to say is that the dark matter is just it behaves like normal matter with respect to gravity. So we can use our theories of gravity to describe its behavior. And it doesn't interact with light. So it's pretty simple stuff. We can just apply gravity to it, and it doesn't do anything else. Just responds to gravity. And then we're going to assume the simplest kind of dark energy, something that's it's constant. There's this pressure pushing space apart, and it's the same everywhere in the universe, and it's the same at all times. So it's a constant. Given this model, it's actually very simple to build a simulation of this universe. Because it's essentially, you have this constant pressure, and then you have stuff that interacts via gravity. So all you need is a set of initial conditions. You need to know what the initial density distribution of the early universe was, and we actually can measure that from the cosmic microwave background. So we have a measurement of how things start out, and then we need a theory of gravity. So you can take Einstein's theory of general relativity with a cosmological constant, and that gives you a theory for how those initial conditions should evolve with time. Right, so then all you need is lots of computer time on a big computer, which is non-trivial to get, and you can then actually build a relatively straightforward simulation of how the universe evolves. So this simulation here starts out at early times with things being pretty uniform. This is essentially, but it's not completely uniform. You have little places that are a little more dense than other places, and this initial setup is informed by what we see in the cosmic microwave background. Okay, now all we're going to do is turn on gravity, turn on general relativity, and let time run. And what happens quite quickly is that places that were a little bit more dense than the regions around them pull in stuff around them. They have a stronger gravitational pull, so they tend to get denser and denser with time. I should say this simulation here is just showing dark matter. Okay, there's no normal matter in it. Dark matter is 85% of the mass in the universe, so that's not a terrible approximation. What looks bright is essentially high density. So the brighter something is, the higher the density of dark matter in that region. But this is just a map of dark matter. Okay, so if we then zoom in to just some subcomponent of one of these simulations, we can watch a smaller region of the universe forming in detail. And what you see is from this early relatively uniform distribution, you quite quickly get little clumps. And then those clumps are pulled together. So you start getting merging of these clumps, and you wind up with these streamers of mass, of clumpy mass out at larger distances, all of which are eventually being pulled in. And so you wind up with a system where you have a kind of a big clump of mass at the center that's just being pulled together by gravity. There's no other physics here. This is just gravity, right? That then gives you some clumpy structure at late times. And we then just take a snapshot of that at the end. You run your simulation up till the present, and then stop it. You just take a snapshot there. What you see is that you have these big concentrations of mass. The stuff clumps together because gravity has pulled it together. And then there are these little kind of substructures, subclumps, that are orbiting around this central big clump. And so this is just zoomed into a very small part of the simulation, but we can zoom out and look at how things look on larger scales in the box. And you see these big clumps are connected together by this filamentary structure. This is sometimes called the cosmic web. And this is, if you could go out and take a picture of what the dark matter in the universe looked like, this is what our model, this is what the cold dark matter theory predicts the universe should look like in dark matter maps. So there's these sort of filamentary structures, and then you have these big empty spaces where there isn't very much stuff. And all of these little clumps in here are little concentrations of dark matter. We call them dark matter halos. Right, and if you zoom out again, what you see is actually on large scales, space is relatively uniform. This region over here looks pretty similar to this region over here. So there's kind of this model has predictions for what is the scale of clumpy structure that we should see in here. All right, so that's all, and we can actually, sort of a side point I want to make is we can test this model for the universe, test our kind of cold dark matter plus Einstein's gravity model by then comparing the distribution of clumps in the simulation to the distribution of galaxies that we actually see in the universe. Right, so these red things here are maps from the simulation of where the galaxies are. The blue and purple things here are maps from the observations where actual galaxies are observed. To do this, of course, we have to do something a little complicated because we have to understand how to put galaxies into the simulation. The simulation here is just dark matter. So we have to make assumptions about how galaxies live in those dark matter halos. But those can be informed by simulations. So simulating a big cosmological scale thing like this, we can do it with dark matter because dark matter is simple. All we need is gravity. We just have to model gravity because it doesn't interact through the other forces. As soon as we start putting normal matter into the simulations, things that interact with light, it becomes much more complicated. You have gas, and the gas can shock heat, and the shocks can radiate, so things lose energy and heat up and cool down, and the astrophysics becomes very complicated. It's a much more complicated model. You can't build a simulation this big. What you can do, though, is you can zoom in to one piece of this dark matter simulation here. So we're just going to take some subcomponent of it, and we're going to wind it then back to very early times, and we're going to put gas in, and actually then model how the gas and the stars evolve in this small box. So that's what this movie simulation is doing here. So what you're seeing here in blue is gas, and then the little dark blue and yellow and eventually red dots are stars, are little clumps of stars that are forming here. And the gas is moving within this dark matter framework, and you can see mass streaming in from large distances. We had to use our big cosmological box to get that to happen. But once you put gas in, you actually start modeling where the galaxies form, how the galaxies form, what they look like. And you can see, again, there's this gravity essentially is pulling things in from different directions. And when you start getting dense enough clumps of gas, gravity pulls, those collapse under their own gravity, and they start forming stars. And just by following how the mass moves in along these filaments in the early universe, you wind up with these rotating spiral structures that they form big disks of gas. Those disks of gas form stars. Smaller bits of stuff keep getting pulled in at late times, and you build up a galaxy slowly over time that has many of the properties that we see in galaxies today. Right, so you can then compare snapshots. You can compare snapshots from the simulation of the earlier times and later times of what these simulated galaxies look like. And you can compare them to pictures from the Hubble Space Telescope Ultra Deep Field. So these are relatively high redshift galaxies. And you can see we see a lot of similarities, right? These simulations do a pretty good job of producing the kinds of structures that we see in normal galaxies. And the main ingredient is just you add gravity, and let it pull things together. All right, so the simulation I just showed you does quite a good job of producing these spiral kind of galaxies that we see here. But what about these other guys, right? These very bulgy galaxies that don't have a lot of disks. We don't see a lot of star formation going on in them. How do we make them? Well, you can ask, what are the things that you have to do? Like, what are the differences between these galaxies? So if you want to get from a spiral to one of these spheroidal galaxies, we have to turn off star formation. Okay? So we don't see clumps of forming stars in these galaxies here. So we need a process that's going to turn off star formation. That means we have to remove the cold gas that the stars form out of, because we don't see a lot of cold gas in these galaxies. And if it were there, it would be forming stars. We have to destroy the stellar disk. We don't see big stellar disks in most of these things, right? We've got all these stars that are here in a rotating disk. We have to somehow disrupt that disk. And we have to build a really big bulge. So some of these galaxies here with disks don't have a sort of spheroid component. We have to make this big ball of stars to do that. So one way the best way astronomers have found to do this, again using computer simulations, is by colliding spiral galaxies together. So this is a simulation here that tracks the process of two spiral galaxies interacting with one another. And what you're seeing is these simulations have actually been done to try to reproduce how galaxies should actually look. So they have stars. What you're seeing with these, in blue, you're seeing bursts of young stars forming. So you're seeing sort of you're seeing star formation triggered by interactions between these galaxies, and gravity pulls them together. One of the things that happens during this merging process is that the stars that are sort of in rotating disks and are relatively orderly, those orbits get very much perturbed by the tidal interactions between galaxies. And so instead of having these things that started out as nice, flat, rotating disks get completely mixed up and sprayed out into these complicated sets of stars. So these stars are now not, the orbits of the stars are no longer all orderly going around a disk. They've been kind of scrambled in all different directions. And the other thing that's special about these simulations is that they've actually tried to include the effects of dust. So where dust should be in the merger remnant and what it looks like. So you can see there we're looking through a dust band. We see these dark, obscuring chunks of a galaxy. So we can take the results of these kinds of merger simulations and we can compare them to visible galaxies. And they look pretty compelling, right? This merger activity has destroyed the stellar disk, has mixed up the orbits to make these big fluffy balls of stars. We do sometimes see dust, where we saw some dust left in this merger remnant here. We see these dust bands, but it depends on the orientation, right? We saw that as we looked in different directions, some ways in the simulation we saw dust, in some places we didn't. More than that, we actually also see pictures of galaxies in the real universe where this merging activity is going on. So these are Hubble Space Telescope snapshots that are catching galaxies in the act of interacting with each other and disrupting each other's stellar orbits, and eventually forming these sort of messy, blobby things that over a large period of time will kind of settle down into these nice spheroidal-looking objects. So an interesting point is that this is actually the future of our own Milky Way galaxy, that movie that we just saw. So in the local group of galaxies, we're here in the Milky Way, but we have a friend, right? The Andromeda Galaxy, our neighbor, from whom we've learned a lot about what spiral galaxies look like. These two galaxies are gravitationally bound. So right now they're in an orbit around each other. And what will happen over the next few billion years is that those orbits will close in, and we're actually eventually going to merge with the Andromeda Galaxy, similar to what happened in the simulation that I just showed you. So artists have fun with this. They make pictures of what the sunset sky might look like as Andromeda approaches. But in addition to beautiful sunsets coming, you can ask, is this something we should be worried about? If we're still around 2 billion years from now when this merger is happening, what is it going to do to the sun? The answer is it's not going to do very much, actually. It probably won't be a problem. And that's because galaxies are mostly empty space. The stars are really, really small and really far apart. So it's like if I scoop up a handful of sand and you scoop up a handful of sand and we throw sand at each other, we both wind up with a face full of sand. Because the sand particles are so small, they mostly just pass right by each other. The chance of any two hitting each other is very small. This is what happens with galaxy collisions. So our orbit around the center of the Milky Way will be different. We'll be in a different orbit. But the Earth, Sun system, and the other planets are unlikely to be perturbed. So we'll just kind of keep doing our own thing, but we'll just be moving differently around the center of our galaxy. All right, so just coming kind of back and checking in with what I said I was going to tell you. We talked about what a galaxy actually is, and looked at multiple different kinds of galaxies that are out there, which allowed us to come up with a definition of what a galaxy is. A galaxy being this mass of stars that are held together by their own gravity and also by the dark matter that is associated with them. We looked at the different ingredients in galaxies. So we saw that there are stars that provide a lot of the light, but there's also gas, hot gas, cold gas. There's dust that obscures the light. So when you see those dark bands in the Milky Way galaxy, when you go out at night and look at it, what you're seeing is dust obscuration. You can't see the stars behind the dust. We've seen that that big galaxies harbor black holes, massive black holes at the centers of the galaxies, and that those black holes know something about how the galaxy formed. So bigger galaxies contain bigger black holes. Finally, we've seen that a lot of the galaxies are actually dominated by the dark matter component. It's the largest contribution to the mass, and that allows us to build a framework, a very simple, just applying the theory of gravity kind of framework for how galaxies assemble over time. So I want to just end with a little bit of perspective. This is a picture of the night sky. We're not used to seeing this many stars when we go out and look with the naked eye, so actually one of your favorite constellations is hiding in this image, and it's not really actually that easy to pick out. But in the upper left corner, we have Orion. Right, so here's just a piece of the sky. We can ask the question, what happens if you zoom in to a relatively empty region of space? So we're looking now kind of in between all the different stars in our Milky Way galaxy. We're using bigger and bigger telescopes to focus in and take images of smaller and smaller pieces of the sky. And we're going to pick this little dark region here where there's just not much going on. And we're going to point the Hubble Space Telescope at it for days and just see, what does Hubble see in the empty space? When we zoom all the way in there, what we see are galaxies. Basically all the way out. All of these little things in here are galaxies, every single one of them. This is just a tiny, tiny piece of the sky. So they picked the Hubble Deep Fields to be a piece of sky that was empty. That was all they knew about it, is that it was basically empty, and they just pointed the telescope there for a big chunk of time. So any piece of sky that you pick, you point at it for long enough, take a deep enough exposure, and you see galaxies all the way out. We spend a lot of time worrying, or some of us at least, spend time worrying about how many people there are on the planet, right? There's 6 or coming on 7 billion people on planet Earth. For every person on planet Earth, there are 100 galaxies out there. And every one of those galaxies has 100 billion stars in it. So there's an enormous amount of space out there. There's an enormous number of worlds out there in those distant galaxies. What I want to leave you with is just a picture, an image of the Hubble Deep Field. And there are a few things in here that are stars. You can see them by their characteristic diffraction spikes. But basically every dot that you see here is a galaxy. And one of Carl Sagan's famous statements is that there are as many stars in the universe as there are grains of sand on the beaches of all the beaches on the Earth. And this is actually a problem that we give some of our intro astronomy students to calculate, is this actually true? And it turns out that it is basically correct. Carl Sagan knew what he was talking about. So there are out there, in all of these galaxies, there are stars uncountable. Stars, as many stars as there are grains of sand on all the beaches of the Earth. And even if you look at what looks like the most empty piece of the sky, you look far enough out there, it's full of galaxies. And I find that very encouraging, both in terms of the future of the human race and our space exploration, and also in terms of my own work, because I study these things, and there's an infinite number of them to study. Thank you very much.
Thanks, Genevieve, for a very interesting talk. Those of you who want to go back and watch this talk again or pass it on to your friends or indeed see any of the other talks in our series, you'll see Chris and James here at the back faithfully recording these talks every month. You can go to our website and catch up with the talks and get on our mailing list. And again, come back next month to hear more about the dark matter. But I'm sure there are some questions from the audience for Dr. Graves here at the back.
Way in the back, is there a chirality about the universe?
A chirality, in terms of, is there a preferred direction of rotation? So, I have sort of two answers to this question. One is that if any large-scale gravitationally bound system where things are moving, if you don't start out with everything exactly, perfectly, completely symmetric, as things pull together with gravity, any existing angular momentum that they have will spin them up, right? Well, so and there's also, people have actually, there's a project called Galaxies Zoo, where people have gone out and looked at pictures of many different galaxies, and what they see is that, some spirals rotate this way, some spirals rotate that way, and people have counted up how many of each kind there are, and they find that there are asymmetries. They also find that when they put the button that people click on to make it clockwise on one side, and the counterclockwise button here, they get more clockwise galaxies. If they switch the buttons, they get more counterclockwise galaxies. So there's a sociological part of this as well, not beyond actual physics.
Calm down.
Yes?
How do you account for the relatively stable formations of gas? Look at a Horsehead galaxy and it's still there next year. Doesn't gas move about?
It does, and the Horsehead Nebula is moving, but the scales, the speeds that it's moving at are slow compared to the scale of the thing. It's an enormous structure. And the kind of time scale, so the Horsehead Nebula will be gone in 1 million years. But 1 million years is a very long time scale from the perspective of human beings.
When you look out of the deep field, if you had telescopes powerful enough to see much farther out, would the entire surface of the observable universe be papered with galaxies? In other words, are there enough galaxies out there that in every direction there is light coming towards us?
Right. The answer is no, because the amount of space that we can see is finite. We can only see as far as there has been time for light to travel from the early universe. So we actually don't get to see out infinitely distant. We can only see out 13.7 billion light years. And there may be universe, there probably is universe out there that's farther away than that, but we can't see it because the light has not had time to get from there to us.
So within the spherical shape of the Big Bang, that is, we go back 13.7 billion.
We've got dark space. Now, if you point a telescope there even longer, there will be some galaxies in there, but they get fainter and punier as you go out. Yes?
When you were talking about the balance between gravity
Mm-hmm.
which you can use the term radiation pressure.
Mm-hmm.
What forces? What are we talking about?
This is not something I'm an expert on, so I'll give you my best answer, but I'm not 100% sure it's correct. I think it is essentially interactions between photons and the atoms that they are running into. So essentially, some of them are on their way out from the center. The photons are produced by nuclear fusion in the center of the star or the sun, and they're moving out. And as they move out, they bump into, it's very dense, they bump into another atom. They get absorbed, and then they get re-emitted. But when they get absorbed, they essentially transfer a little bit of momentum to that atom that's absorbing them. And because the net flux is out from the center, that produces a net pressure, essentially, of those interactions it's pushing outward.
NASA's used this principle for solar sails, for example, where you have a large structure out in space, and although light has no mass, and although it carries very little momentum, it does actually result in a net pressure, which can potentially power a spaceship.
Yes.
In your simulation, you showed the universe from the beginning out to the current time. You showed the any other part. Was that redshift?
Yes, I'm sorry, that was redshift.
Relativistic redshift, I assume.
So the redshift is a measure of essentially the expansion rate of space, and it's a kind of a funny scale in the sense that you go from redshift 0, where we are now, to redshift 1, and that's about half the age of the universe. You go to from redshift 1 to redshift 2, and you're now back at like 95% of the age of the universe. And then redshifts 2 to 3,000 are between that early piece of the universe and where the cosmic microwave background is. So it's a scale that's very compressed. It's very compressed at the early part of the universe.
And a follow-up question on that simulation, that included dark matter.
That was only dark matter, in fact.
What happened if you do it without dark matter?
So without dark matter, essentially there's a lot less stuff, and structures don't form very efficiently because there isn't enough stuff to pull things together. So you get a very different, that kind of web of stuff that I showed you at the end, you get a very different pattern of the distribution of matter if you don't have dark matter in the simulation.
So no galaxies, no stars, no people, no world, if there were no dark matter.
Well, or very differently. I haven't run, so those are not my simulations. I haven't run them without dark matter. I don't know what they look like. Yes?
So a couple of questions on gas. You talked about hot gas and cold gas.
Mm-hmm.
And could you clarify, how the two play a role in star formation, and also how the gas heats up? If you don't have, fusion presumably in gas, so what causes it to heat?
So we believe stars form out of cold gas. So essentially, if gas is heat, you have essentially thermal pressure. Again, you have these atoms and molecules bouncing around and kind of essentially bouncing off of each other, performing pressure that holds the gas cloud up. If the gas cloud cools off and those random thermal motions decrease, eventually gravity wins, and the cloud starts to collapse in on itself, and you get this kind of runaway collapse. Things get denser and denser. Eventually, things get so dense that as they get denser, they heat up again, and they get hot. In some cloud collapses, it gets hot enough at the center to ignite nuclear fusion. This is how a star forms. So this gas collapses in, a part of it essentially forms a star, starts this nuclear fusion process, and that suddenly now is producing a lot of energy. That energy then starts radiating out. And what happens is that the radiation coming out of the star then heats up the gas around it, starts blowing the gas out again. So a lot of those beautiful Hubble Space Telescope pictures of pillars of dust, and you can see sometimes small stars forming, and you can almost see, in the pictures you can even sometimes see what's happening, which is that these winds and the radiation streaming out of these hot young stars is actually blowing back the gas, heating it up, blowing it away. So the hot gas is actually heated by the young stars that had been born inside those clouds. So these cold clouds actually destroy themselves. They build stars, and then those stars destroy the clouds they formed out of.
So if the gas mass compresses, nuclear fusion starts. So some of the gas is ejected. Does the star also expand then and come into equilibrium? Or?
Yes. So I think the stars, I don't know a whole lot about the early star formation process, but there is a process of the star core forms, there's mass is still kind of streaming in onto it, it accretes mass, eventually that process stabilizes it, it kind of cuts off its own supply of mass by the radiation coming out of the star.
There's a young man at the back here.
So black holes don't suck things in. Black holes behave, if you're at a reasonable distance from a black hole, it behaves just like anything else. So if our sun turned into a black hole like that, the Earth would just keep moving around it. It wouldn't fall in because the gravitational force of that black hole is the same. Even whether it's a star or a black hole, however you put that mass together, it has the same effect. Now, of course, we would lose the sunlight, and we would notice for other reasons. But black holes, they're only dangerous if you get very, very close, right? But that's true of any mass, right? If you get really close to the sun, you can get caught in the orbit of the sun, pulled into the sun. That's not a good thing either. So black holes, they don't go out vacuuming stuff. They behave like any other mass. What's different is what happens if you get really, really close to the center where you're essentially falling in. What happens to you when you fall into a black hole is different from what happens if you're falling into a normal star.
What's the speed of gravity?
The speed of gravity. Gravity seems to propagate through the universe, I think, at the speed of light. Is that true? Gravitons, right? So they're essentially, if you're here and you're feeling some gravitational force and there's a thing here, and it moves. Say you could just move it instantly, you wouldn't know that it had moved. You'd keep orbiting as if it were where it was. It would take some time for your perception of where that thing is to catch up.
The sun disappears. It will take 8 minutes before we feel the gravity go back.
Exactly. Yes?
What exactly is dust? What is it made of, and how did it get there?
Dust, we think that dust is a collection of heavy elements, so silicates and other little metal atoms and particles. So you get very small bits of dust formed in the outer parts of cool stars towards the end of their life. You get some molecules formed there, which then sputter out. But actually, one thing we don't understand very well is how grains grow. Or at least I don't understand this very well. So you make some very small dust grains in the outer parts of stars from heavy elements, but then they can collide and stick together and build bigger dust grains, and there are parts of that process that are very poorly understood, and in general, it's not something I know a whole lot about.
The particles are kind of similar size to the particles in cigarette smoke, and really kind of it's sort of smoky stars that are burning at low temperature, and then also in supernova explosions, you get a lot of dust production as well, sort of where the temperatures are kind of cool enough for solids to be able to form essentially, but only in really pretty small grains.
The simulations of two spiral galaxies merging to form an elliptical, over what time frame?
Yeah.
And the second question is, what happens to the cold gas that we used to be in these spiral galaxies?
Yes. So the first question is easy to answer. It's a few 100 million years. These merger processes, right? So it takes about 1 billion years to go from having the two galaxies near each other to having something that looks like a calm, normal elliptical galaxy. So that simulation that I showed you ran over, 500 or 600 million years. So that's the easy question. Second question: where does the cold gas go? This is not fully understood. Okay, so this is actually one of the big unsolved problems in galaxy formation, is how do you actually get rid of the cold gas and shut down star formation? People build merger simulations. You get some star formation happening, and those supernova explosions heat up and push out some of the gas. But in massive galaxies, they can't impart enough energy to the gas to actually get it out of the galaxy and keep it out. It falls back in again pretty quickly. So one mechanism that people have invoked for this is activity from these big, massive central black holes. Essentially, if you let some of that gas in the merger process, that gas tends to funnel to the center of the galaxies. The black holes are sitting there. If you can dump some of that matter onto the black hole, you get quite a lot of energy out. The problem is that we don't know how, and we see galaxies that have these jets, radio jets of material being spewed out of massive black holes. So we see these jets. We know that there's enough, you can sort of physically calculate how much energy is available from the process of dumping mass onto a black hole. It's enough energy. What we don't know how to do is then actually couple that energy to the gas in the galaxy and blow it out. So there are people who do simulations where they just say, we're going to assume that 10% of that energy it gets transferred to the gas in the galaxy. And that's enough energy to blow it out. But the physical mechanism for how that transfer happens, or whether that actually is what's going on, is not well understood. So we still don't actually have a fully satisfactory model for how that process happens. Yes?
They talked about different universes and different dimensions. Is it possible that we have other universes opposite from ours in different dimensions?
Is it possible? I think the answer is yes. I don't think that we know. I don't think that we have a convincing theory yet for the sort of very large scale, how did our universe form? How did the Big Bang happen? Is string theory a correct, or brain theory a correct description of what's happening on larger scales? I think the basic answer is we don't know.
It's speculative, right?
It's speculative to the point of being philosophical, I would
There are
say.
some predictions that some of those theories make. That there may be imprints from some of the extreme theories have been ruled out by observations, but it's a very difficult thing to test. Sort of what's the imprint of these alternate dimensions on our own universe. But
I think it's safe to say there is no evidence that that is the case. But there are theories, some of which are quite elegant theories that say that that could be true, and we don't have a way to observe whether or not it's true.
If the faster than light neutrinos thing holds out,
That'll be very cool.
interesting. The faster than light neutrinos experiment that some of you may have heard about, which is most scientists think is probably just
But they've measured again, right?
Yeah, the same group of measures.
Same group of measured again. So
It's intriguing. I mean, there are hints that maybe there's some interesting physics in it.
Yes.
What's happening when they say the star is dying?
The star is dying. Okay. So stars die in different ways. Depends on how big they are. Really massive. I talked very little about stars. I thought about going through stellar evolution and decided it was that's another talk. But really massive stars burn much, much hotter and faster than smaller stars. So really massive stars burn through their fuel very quickly. And what happens is they quite quickly, they fuse hydrogen into helium, and they fuse helium into heavier elements, and they eventually get to a point where they can't generate energy by nuclear fusion. They essentially have fused all the way up to iron. They have a core made of iron. And iron is this special element. It's essentially the sort of lowest energy state. You can take smaller things and fuse them together to get energy out, up to iron. And then you can take heavier things from iron, like uranium or plutonium, split the nuclei apart and get energy out. When you get to iron, you can't gain energy by going either way. It's sort of your lowest energy state. So a star that has iron at its center cannot fuse that into something that will produce energy. So then it doesn't have energy, it doesn't have anything to hold itself up. It still has gravity pulling everything in, and it no longer can produce the energy to hold itself up. And with really massive stars, what happens is that then they collapse in on themselves very dramatically, and then there's kind of a bounce out and an explosion. This is called a supernova explosion. This is the particular types of supernovae are produced this way, and the star explodes spectacularly. Depending on how big the star is, you sometimes have some compact core left. So you have a lot of stuff thrown outward, but sometimes you can wind up with a neutron star or a black hole left at the center of the supernova explosion. Smaller stars, like the sun, never even get up to burning iron in their cores, but they're not dense enough. They don't get hot enough, so they essentially get to a point where they run out of fusion prospects because they've sort of burned up as much as they can, and they're not hot enough to ignite higher level nuclear fusion. So again, they run out of fuel. Again, they sort of collapse in on themselves, and some part of it's thrown out, but essentially their gravitational force is not strong enough to actually produce a supernova explosion or a neutron star or a black hole. So in that case, you wind up with a white dwarf, which is another degenerate state of matter. So you have this like small, hot thing left at the center and this big shell of gas around it that it's blown out. And that white dwarf will then illuminate the gas around it. And you can see these kind of glowing rings, little white dot at the center, glowing ring around it, called a planetary nebula. And then that white dwarf will then slowly fade out as it has a heat reservoir. And once it has exhausted its heat, it will just fade away.
What do you call that?
It's a white dwarf, just a cold one. Yes?
Would you share an astronomer's fantasy with us if the James Webb actually goes into orbit? Current estimates put it about 2018, which means it'll probably be 2025.
Right.
What would you like to see and talk about?
So the James Webb, I think that there's several really exciting things that James Webb is going to do. One of them is that the kind of pictures that we take with Hubble in the relatively nearby universe, James Webb will be able to take in the very early universe. And it's partly because it's a bigger mirror, so it can see fainter things, but it's in large part because it's been optimized for infrared wavelengths. So what happens is the light, when you start looking in the more and more distant universe, galaxies actually put out a lot of their light in the optical range. That's where they're very bright. And they're not very bright in the ultraviolet. And dust also. Dust, in large part, that's because of dust. Dust absorbs ultraviolet light very efficiently. So what happens is if you have your optical light all gets red shifted into the infrared, You can't see it in the optical wavelengths anymore. And that higher frequency ultraviolet light that would be in the optical wavelengths is now all obscured by dust. So you just can't see those galaxies in the optical because they are so faint. So James Webb is going to be looking out in the infrared where actually there is some light to see from those galaxies. So we'll be able to see very distant, faint galaxies and see them with reasonably good resolution, take the kind of beautiful pictures we take with Hubble more nearby at higher redshifts. So looking back into the earlier universe. That's one very exciting thing that James Webb will do. Another thing that it will do is for things that Hubble can just about barely see, James Webb will be big enough to take the light there and put it through a prism and get a spectrum. I showed you one spectrum of the sun here. One of the things that's very exciting about spectra is there's all kinds of complicated sort of physical measurements you can make from them. So from spectra, you can tell how fast a galaxy is forming stars. You can tell how many heavy elements they're in. So how many generations of stars have been burning heavy elements, have made iron and carbon and things like that. You can see black holes at the center that have mass falling onto them. They have a very characteristic pattern of emission lines. You can start making more detailed physical measurements. You can see orbits. You can measure how fast things are orbiting in the galaxy. You can't do that just from a picture, right? So once you get spectra, there's a huge amount of physical information that's not available just from an image. James Webb will be able to get that information for galaxies out at, when the universe is a small fraction of the age it is now. So that's very exciting. I think the other place where James Webb is really exciting is actually the idea is hoping to take direct images of planets around other stars. So that's very different from anything I was talking about here, sort of different scale of astronomy. But currently we don't have the capabilities to directly image and get information about planets that are orbiting other stars. And James Webb, I think, will be very good for that.
Let's take one last question.
Yes, in the back there. Yes? Okay, so, and I should say, I'm happy to stay and answer any other questions that people have everywhere, but, so if you have questions that you want to answer, stay and ask. We can't see planets in other galaxies. We actually struggle to see planets in our own neighborhood of our own galaxy. So we can see planets on sort of nearby stars, but we can't see planets at the far sides of the Milky Way. And we certainly can't see individual stars in other galaxies. So how planets form? We think, and again, this is not my field of expertise. So.
Meredith Hughes, who spoke last month, the video's up on the website.
Right. So there's lots of details there on the web if you want to see that. But basically, you have this cloud of gas we were talking about before with star formation. The gas is collapsing in on itself. And eventually, in the central part, it gets hot enough to ignite nuclear fusion. But at the point at which this happens, there's this cloud of debris and stuff that's still streaming in onto the star. And for reasons that are a little so you have stuff streaming in. So as I sort of mentioned before, anytime you have stuff moving in, you get angular momentum that builds up. So you wind up with stuff that's rotating. So these stars wind up being surrounded by a rotating disk of stuff that kind of settles down. And if there are heavy elements in those disks, then those little particles of dust start sticking together, and you start forming these little rocky chunks. And again, there's a gap. We know how to make, people know how to make kind of small bits. And then once it gets big enough that it actually starts to have a gravitational effect on the stuff around, then these little planetesimals start pulling stuff in from the disk that they're moving in. They start pulling in bits of the disk, and they grow into planets. There's a gap in our understanding of how to get from the little rocky bits, the little tiny bits, to things that are actually big enough to gravitationally pull in stuff around them. But the planets seem to form in the disks of just debris and junk that are rotating around these young stars as they form. Eventually, the young stars get hot enough that they blow out the remaining material in the disk. So once you form planets, you essentially use up a bunch of the material, and whatever's left is carried away from the star. So planet formation probably happens in the early phase of the life of a star. So water is one of many. It's just a combination of chemical elements. So the hydrogen in water mostly comes from the Big Bang. The oxygen in water is all produced in previous generations of stars. So you have to have, early stars were fusing hydrogen into helium and helium into heavier elements and making oxygen. All that oxygen was produced in stars, was blown out in supernova explosions as debris, and then, somewhere along the way, it met up with a couple of hydrogen atoms and made water molecules. Water is a molecule that can only exist at relatively low temperatures, so you're not going to find it in the sun because it's too hot there. It just breaks apart the bonds. But anywhere where you have oxygen, there's always hydrogen around, a lot of it in the universe. If you have oxygen and you have the right kind of temperatures and conditions, you can form water molecules.
Let's end the open discussion here again, but if you do have other questions, please come up and talk to Dr. Graves.
I actually grew up here in the Bay Area. I was born in Berkeley in Alta Bates Hospital, and when I was about 4, we moved all the way to Albany, and I went all the way through the Albany Public Schools. So this is essentially me coming home, being back here in Berkeley. I've been a research fellow here for the last 2.5 years. I've got 1 more year to go, and then I head off to the next phase, and I don't know what that is yet. I'm applying for jobs right now, so we'll see. I did my thesis work at UC Santa Cruz, working with Sandra Faber there, on galaxy evolution and studying galaxies in the local universe in particular. What I'm going to talk to you about today is to try to give you a large-scale picture of what galaxies are, how they relate to us in terms of the sort of the scales that they occupy versus the scales that we occupy, which are very different. And in particular, I want to convey the fact that galaxies are not static. They are entities that evolve in time on very slow, very long time scales, but they are continually changing their character. And our galaxy today is not going to be the same as our galaxy in the far future. So this is a look at how those processes happen in galaxies. How many of you guys have been out on a dark night somewhere far away from the Bay Area and actually seen the Milky Way in the sky? Okay, good. So most people, if you haven't done it, you should take the opportunity sometime when you're driving across the desert. You need a dark night because it's quite faint, but you get this solar system. And as we move outwards, eventually we're now only just now getting to scales where we can actually see other stars moving with respect to the Earth. So essentially the stars are all so far away that you have to go to very large distances before they actually start to look like they're in different places in the sky. And you can see that as we sort of zoom out here, we're in this collection of stars that is producing a bunch of light, which from a distance looks quite smooth. But if you actually go in and focus in, all of that light is coming from hundreds of billions of stars that are packed together in the Milky Way galaxy. Then what happens is if you get out far enough, there aren't any more stars. These dots are actually maps of other galaxies in the universe. So the stars really are concentrated within a galaxy, and then in between galaxies, there's very little. We don't really see anything there. So they are sometimes referred to as island universes. There's this island of stars that are self-connected, but that are isolated from other things in space. A challenge was trying to study our own galaxies, but we're in the middle of it. So we don't get a very good picture of it. We can't see it from the outside from a wider perspective. We just see kind of close in what's going on, and we have to look through a lot of junk to see what's going on. So one way that astronomers study our galaxy is actually by going to a separate galaxy. So our nearest neighbor, the Andromeda Galaxy, is part of our local galaxy group. Like the Milky Way, it's a spiral galaxy. It has many similar properties. So what's nice about it is it makes a good proxy for studying our own galaxy because we're outside of it and we can see it from that exterior perspective. However, if we put back up this picture of the Milky Way here, we can see that there's a lot of similarities between these galaxies. When we see bright patches that tend to be sort of yellow or red toward the center of the galaxy. We see bluer light coming from stars farther out in the galaxy. We see that in Andromeda, and we can kind of map that mentally onto what's happening in the Milky Way here. We also see these dark clumps in both galaxies. In our own galaxy, we just see these dark bands. If you then look at Andromeda, you can see that those dark bands are actually distributed in spiral structures and in the spiral arms of the galaxy. And the other thing is we also see these bright pink knots of glowing gas. And we see that both in our galaxy and in the Andromeda galaxy. So there are many ways in which Andromeda is a good proxy for studying our own galaxy. And we can see it from the outside, so that helps us try to understand what's going on in our own galaxy. Right, but not all galaxies look the same. This is just a gallery of Hubble Space Telescope photos of various galaxies in the relatively nearby universe. And you can see, like, the galaxy in the middle there is one that's like the Milky Way or Andromeda, has spiral arms, has spiral structure. We see these dark dust lanes. But there are galaxies that this spray of kind of faint, wispy stuff across the sky. This is an image that was taken in the desert in Arizona. And if you look at it with your naked eye, you see something that is black and white. You basically just see there are places where there's light and places where there isn't light. And that's in part because the color sensing part of your eye is not very light sensitive. So in faint conditions, you basically see in black and white. But if you have a digital camera and you can take an extended time exposure, you can actually get colors. There are actual colors in the Milky Way, and things look quite different when you add color. So now we can see that, I'm going to turn the lights a little bit. Right, so you can see that there are bright patches and then there are dark patches in the Milky Way. And there's this it's a streak across the sky. We even have these little clumps of bright red light that are scattered through there. Some of the light looks bluer, some of the light looks yellower. So there's a whole bunch of different stuff going on in the Milky Way. And that's in part what we're going to explore today, is what all these different components of our galaxy are. All right, so just a very brief outline. We're going to start by just talking about what is a galaxy. And then go on from there to think about what galaxies are made of. What are all the different components that exist in galaxies, and how do they relate to one another? And then move on to talk about essentially how do you make a galaxy? Where do they come from? How do they form? How do they evolve with time? And how do you make different kinds of galaxies? Because not all galaxies in the universe look the same. And then finally, we're going to end with a little bit of context, just trying to understand where galaxies are in the universe and how many of them there are out there. All right, so what is a galaxy? Well, just to start with some sort of scale perspective, we're going to start with something that is hopefully a familiar scale to everyone. I'm going to turn the lights down again here. Which is the planet Earth, right? If you've been on a long plane flight, you have experienced, to some extent, what the scale of the Earth is. It's big, but you can get around it. We can move around it in human amounts of time. What we're going to do now is zoom out from the Earth that is this familiar place to us and look at how it fits in to the Milky Way galaxy that we were seeing there on a dark night in the desert. What this is showing you right now are the orbits of various man-made satellites that we've launched into space that are orbiting around the Earth, some of them in close orbit, close in, and then some scientific instruments that have larger orbits farther away from Earth so that we can get them out into darker parts of the sky. If we keep zooming out, you can see there the moon traces out an orbit around the Earth that looks big compared to all the satellites, but then when you start to scale out toward the scale of the solar system, it's really quite small. The moon is very close by. So continuing on, now we're looking at essentially the entire scale of the solar system. This is about 1 day's worth of light travel time. So light takes about a day to get from the sun outside of